Happy day and welcome everyone. Today's lesson is on oxidation reduction reactions. Now, this word oxidation, a lot of you have already heard, and you can very easily kind of figure out what the definition might be. So if we say the word oxidation, I'm sure you're thinking it's got to have something to do with adding oxygen, which actually is one of the definitions of it. But there's a second part of it that really brings this into AP chemistry quite a bit more. And I'm going to explain why and what the importance is of oxidation reduction. So if we look at the definition, and a whole bunch of different reactions that take place in our everyday lives are what they call redox reactions. So read for reduction and then the ox for oxidation part of it. So if we look at the definition, it says it's any process in which oxygen combines with an element or a substance. Oh, great. That's what we thought. It was oxygen combining, so it can happen slowly, like the rusting of iron. It can be rapidly, like the burning of wood, for example, but we're adding oxygen to it. A reaction, this is a different one, in which the atoms of an element lose electrons is also called oxidation, which means reduction is the opposite. Okay, so if it loses electrons, we say that it's oxidized, and if it gains electrons, we say that the substance has been reduced. When we talk about the substance, we're typically talking about one of the reactants. That's what we mean by which substance. So it's not just the element or the ion. Well, it could be an element, but it's whatever's on that left side of the arrow. Okay. Why is this important? So oxidation reductions, it's a little bit further, so we're kind of getting a little bit of a head start to understanding what is called electrochemistry. And electrochemistry deals with batteries. And so batteries are something that are very common in our everyday lives, so they've really made a big deal out of understanding electrochemistry in this AP chemistry course. So electricity, when we talk about the word electricity, we typically learn it before we've actually heard anything about electrons. But really, when we talk about electricity, it actually stems from that word electrons, because as long as you can get the movement of electrons, then you can conduct electricity. So we need to have charged particles in order for that to happen. Typically, we've got ionic substances that are inside of solutions, and those ionic substances can actually get charges to carry over, okay? Now, when we'll talk later in the year, when we do electrochemistry, we'll talk about voltage and we'll talk about these differences in charge and how it works. But the number of electrons are really important. And so when we talk about how many electrons are transferred with a reaction that takes place in one of these redox reactions, that's going to be kind of the key thing. So yes, we're learning something that's very specific. And so I wanted to make sure that we can connect that to, like, where does that take place? Why do we even really need to know this? Okay, why is this important? So before we get into working any of these out, I want to make sure that we get some stuff down with definitions. And memory tricks are amazing, okay? So the first thing is, what we're talking about is transferring electrons. That's what redox is. Redox is all about transferring electrons. So this word oxidation simply means that we are losing electrons, or we say that the electrons are on the product side. Now, reduction is gaining electrons. In other words, electrons on the reactant side. So if we were to write some reaction, so W plus X yields Y plus Z, well, we know that things go in on your reactant side. You need to have everything that you're going to use to make the cake in order to make your product cake, okay? And that product leaves, and so I always like to think of it as, once I've made that cake, it's going to be gone. I'm going to lose it because I just ate all of it, okay? So W plus X, those are going to be things going in that we quote-unquote gain, and things that we lose that are lost or released are going to be lost or released on our product side, okay? So I always do this cabbage patch, in on the reactants, out on the products, in on the reactants, out on the products, okay? You know this already because when you learned about thermochem and energy transfer, and we learned about endothermic and exothermic, there are no minus signs in a balanced reaction. You'll never find a minus sign. So what we do is, instead, we say if energy was gained, then we can use some number of kilojoules and call it endothermic. Okay, so that would be endothermic. Or if it's exothermic, we would have our energy number over on the other side. Now, if it were out of the equation, I would call that negative because it's losing energy. But if it's in the equation with a plus sign, then we say that that's exothermic and losing energy, for example. So we do the same thing with electrons. If electrons are being gained, then we would actually write our number of electrons on this side of the reaction. And if electrons are being lost, we would actually write a plus sign here and say that electrons are being lost on our product side. Okay, so what are two ways to remember it? Well, the books, this is not me, this is the books actually all pretty much use Leo the lion says grrr, okay? So we've got Leo says grrr. This is a very popular one. This is great if you are trying to define either oxidation or reduction, okay? So if you're trying to define it, it makes it really easy. We say Leo, so L, lose, E, electrons, Leo, oxidized, okay? Versus grrr is gain, electrons, reduced, okay? So if the substance gains electrons, we say it's reduced. And it's easy as that. Again, that's a definition. You can have a multiple choice question, and then it has a whole bunch of like sentences as your A, B, C, D. And if you know that you look at it and it was oxidized and it basically just says what's happening to it, you're looking for the statement that says that it was losing electrons. The substance was losing electrons. And it's that quick, and this really helps us with it. Okay, so Leo says grrr. Say it a few times, okay, just to get it down. Oil rig works too. So for that, it's just oxidized is losing and reduction is gaining. I don't like that one as much. So I like gain electrons reduced and lose electrons oxidized. Okay. Now this one I did come up with. Here's why. A lot of times what happens is we look at an example, we look at a reaction, and I don't want to work out the entire reaction and balance it and do everything else, but I know that it starts off maybe as a 0 charge and then it increases to a 2. To a +2. All I do is look at the charges, and it says, or it might even say in the sentences in the paragraph of like the story problem, it might say, and it could be a multiple choice problem. It could say something like calcium solid becomes calcium oxide with a +2 charge. Calcium ends up with a +2 charge. And then the question basically asks you what is happening to the calcium. And one of the answers would be, well, if the charge went up, UO, then up means that my charge went up, then it's oxidized, okay? And then the opposite would be if my charge went down, then it's reduced. So this is what I call Dr. And then there's my Dr. UO, okay? So we've got Leo says grr and Dr. UO, all right? So those are the two that are going to help you with remembering this. We'll come back to that in just a second here. So there are some rules that we need to remember. Now, we know that there are, if you look at the periodic table, we know that there are oxidation states. If you look at the key down here on the bottom, it says oxidation states. And so those oxidation states, remember, this is very important, remember what those are is every element in its natural state as seen on the periodic table, where if we look at our key, black means solid, blue means liquid, red means gas, that in its natural state, it is neutral. Neutral means that the number of protons are equal to the number of electrons for that element, okay? So I want to make sure that I can clarify this because some of the elements are special. So we know that the noble gases, for example, do not like to bond ever, okay? They're alone in nature. They're all red. Red means that they're all gases at room temperature. And they are opposite of the diatomics. They are so stable. They're happy with their number of electrons. They have a stable number of electrons. They don't want to lose or gain any of their electrons. Remember, you don't lose and gain protons because that changes the identity of the element. Your protons are who the element is. So these all have 0 charge. But if we look just to the left in the halogens, a bunch of these are called diatomics. The diatomics are the opposite. The diatomics, actually, you will not find them alone in nature. They're either bonded with something else or they're with themselves. There are 2 of them together. They're never found alone, whereas the noble gases always want to be alone, okay? So you know you've got those friends that always have somebody that they're dating. Those would be our diatomics. And then you've got your I'm super confident. I don't need anybody in my life. That was me. That was totally me. I don't need anybody. So those are going to be the ones that are I'm good how I am. I'm not going to give you my electrons. I don't want to take any electrons from you. I am good to go. Okay. So those have 0 charge and those are the kings and queens. So those are our noble gases. All right. So we've got our Brinkelhoff. So again, it's N2O2, F2, Cl2, Br2, and I2, not including the acetine, so it's not all of the halogens. But remember, those in nature will be found with 2s. So if you get something like N2, that would be in the gas state as 0 charge, N2 gas, not N gas, N2 gas. Same thing with like Cl2 gas, 0 charge. Now Br2 would be a liquid. So if we did bromine, that would be a liquid. Same thing with iodine. Iodine is actually a solid, that's black. So it'd be I2 with parentheses S as 0 charge, okay? So just to kind of go over these elements as they exist in nature have 0 charge. So for example, I have a small piece of aluminum foil here. This is aluminum, it's plain aluminum solid. And so we can see number 13, it's black, and black means that it's solid at room temperature. This has 0 charge. This is not charged. So I would have to do something to it to charge it, put it into a compound. So make a compound out of it, and now it's either lost or gained electrons. Well, aluminum tends to act more like a metal. We usually just treat it as a metal, even though it's on the metalloid line. And so that would have 0 charge in this form, but then once it's in a compound, it will lose electrons like the other metals will and have a +3 charge, okay? So that's kind of the way that oxidation states work. Now we remember from honors, these are +1, and +1 for my alkali metals. Remember hydrogen now. Let's zero in on hydrogen for a second here. Hydrogen says that it can be a +1 or a -1. So we didn't really do many situations, but it's called a hydride. So I'll show you that in just a second. But our alkaline earth metals are all +2, and then we've got +3s under scandium and under titanium, +4s, but then we start getting into a situation where we can have variable charges, okay? And that's okay too. We have to figure those out according to the non-metal typically. So now let's come over to the non-metals, which can be a little bit more confusing. So we've got zeros. Under fluorine, the halogens, these are all pretty much -1, but you know that they can have some positive numbers as well. We never used that before. We will now, okay? So I'm going to explain that now. If you get a molecular compound, 2 nonmetals, okay, that are coming together, for example, and I'm not talking about, it could be a polyatomic ion, so like NO3 nitrate with a -1 charge, but it can also be nitrogen trioxide or nitrogen dioxide, which is a pollutant. It's not an ion. It doesn't have to be in solution. It's actually a gas pollutant, okay? And so that's nitrogen dioxide or nitrogen trioxide. Well, in that situation there, whichever element is more electronegative is going to carry the negative charge. Typically, the way it's written is the one on the right is negative, the one on the left is positive. So we go with that. There are only a couple of exceptions, so I'm going to show you what those exceptions are, okay? So we know that for the most part, we've got 0 for the noble gases, -1, -2 under oxygen, -3, and -4, and then we kind of hit the line where we're going off into the metals side of it. Let's take a look at oxygen for just a second here, because oxygen's a little bit different too. We always used oxygen as a -2 charge. If you remember, we would do like CaO. C is a +2 and oxygen's a -2. We would have something like SC2O3. So that would be scandium has a +3 and oxygen's a -2, and then we would crisscross them and get SC3O2, for example. So we know that oxygen we've always used as a -2, but on the periodic table, it says it can be a -1. The question is when. It is -1 in peroxides. And the most popular peroxide we know is hydrogen peroxide. So let's go through these real quick because they're all listed on here. So we said elements in their natural states, as long as they exist solid, liquid, gas according to the periodic table, then those are 0. Again, don't forget your Brinkelhoff, so don't forget your diatomics, because the diatomics are going to be the ones that need the 2s, right? Please don't make helium diatomic. Helium's a noble gas, so helium is not a 2, so making sure you remember that it's H2, not He2. So hydrogen, yes, not helium. Alkali metals, we already said are +1. Alkaline earth are +2. Elements in a compound. So we can see, we'll look at something like FeO, and then we can look at something like Fe2O3. Let's do another compound, but that's molecular. So let's use sulfur trioxide. Again, I'm not doing sulfite, I'm doing sulfur trioxide, which is a neutral compound. These all have 0 charge. Any compound and element that you find in nature is going to have 0 charge overall, but electrons were lost and gained in order to make these equally, right? We can't just have some loss of electrons somewhere. It's between the two elements. Well, we know that oxygen's a -2 charge in all of these situations, okay? None of these are peroxides. Let's look at what that is. Like H2O2, oxygen can have a -1 charge. Otherwise, oxygen's a -2. We also know hydrogen's a +1, except in hydrides, like if you did NaH, well, sodium's a +1, and so hydrogen must be a -1 to make this neutral, for example. Okay, and then I'll come back to the other exceptions. So let's figure out what these are. Well, in this case, FeO, I know it's a 1-to-1 ratio, so if it's -2 for my oxygen, it must be +2 for my iron. And in this case here, I've got a -6, which means this must be a +3, +6. This is rust. Okay, so I've got iron Roman numeral 2 oxide and iron Roman numeral 3 oxide, which is rust. Now in this situation, we've never done anything like this before. Sulfur can actually carry positive charges. Now, we know in molecular they're actually sharing electrons, but the one that's more electronegative is actually going to be pulling the electrons a little bit more. So in this situation, if it's -2 times 3, that actually gives us a charge of +6. Our oxidation number for sulfur is actually +6. If we take a look at the periodic table, well, surprise, they actually have +6 written in as one of sulfur's black oxidation numbers here. So they say it can be a plus or -2, which means the only negative it can be is -2, and then it can also be a +4. Okay, so that's what that means. So we always only did the negatives because we were dealing with ionic substances, but if it's molecular, it can actually take on, it's not a true positive because it's not completely they're sharing the electrons, but it's just that the electrons are spending more time around the more electronegative oxygen in this case, for example, okay? And again, these are 0 charge. I'm going to show you sulfite in just a second here. Sulfite's different from sulfur trioxide, okay? Those are two separate things, two different things. The last thing I wanted to do, one more exception, is N with H, nitrogen with hydrogen, okay? Now, this is weird. Nitrogen is actually more electronegative than hydrogen is. Okay, so then why is it that they write it backwards? We always do that written on the right is your negative and written on your left is your positive. We've always done it that way. NH3, for example, they do not write as H3N. And if you want to guess why, it's because that would indicate that it's an acid. I think that's why, by the way. I've never actually seen it written anywhere, but I'm pretty sure that's why. It's not an acid. So instead they write it as NH3. But if you were to work out the oxidation numbers, H is still a +1. It is not hydride. This is not like the situation of NaH where it's a -1. It is a +1. And nitrogen is a -3. This you're just going to have to remember that N with H is going to be an exception. Okay? So let's take a look at an example of making salt, making table salt. How easy is this? Okay, so let's make salt. So we know that we said if it's in its natural state, like sodium solid and chlorine gas, those both have 0 charge. They're in their natural states. But now we've got a compound. We know that Na is a +1 charge and Cl is a -1 charge. They're both fixed charges, okay, for us. So that's a +1 and a -1, and we're good to go. Well, the question's asking us, is it oxidized, is it reduced, and how many electrons are transferred? Now, normally these redox problems, you cannot balance as easily as we would a normal reaction, okay? And you're going to see the way that they write these is they're written a little bit differently. We can see that they're actually ions, and they're not showing us the entire reaction. They're not giving us everything, okay? And so if they say balance this redox reaction, and you go to balance it normally, unless it happens coincidentally, which it's rare, you have to balance it using the half reaction method, and I'm going to show you that, okay? So let's come back up here. And so all I'm going to do to figure out if it's oxidized or reduced is I'm going to use Dr. Yulo because it's so easy. So all I'm going to do is I'm going to say that my sodium is going from a 0 to a +1. Well, that means that my charge went up. My charge went up. And if my charge went up, then that's UO, and so that means that my Na, and you always use the reactant, you always use the substance on the left side, my Na solid is oxidized because that is my UO, which means my Cl2 must obviously be, Cl2 gas must obviously be my doctor, but let's just check it to see what happened to it. Well, I can see that this went from 0 down to -1, which means that one's being reduced. Okay, so that must be the one that's reduced. Now we have to figure out how many electrons are transferred, but you need a balanced equation to be able to do that, or you need your half reactions. So I'm going to balance this real quick here. I can see that I have 1 Na, I have 2 Cl, so I need a 2 in front of there, which makes it 2 Nas on the left. Okay, so now what I have to do to balance the electrons is this. I know, we already said, that sodium's going up, the charge is going up, which means it's oxidized, which means it's losing electrons. How did I just get that? Because of Leo, okay? It's losing electrons. And reduced is, Leo says, ger, which means that this must be gaining electrons. So you can kind of put those all together, okay? So my O's go together and my R's go together, just to kind of remember that. But how many electrons? Well, it's actually 2 times 0, which is 0. That's easy. And my Na went to 2 times 1, which means the sodium's actually lost 2 electrons total when this reaction ran per mole, okay? Now the Cl2 went from a 0 to a -1, but it is 2 chlorines going from 0, 2 times 0 is still 0. And then don't forget, you have to distribute that 2, so it's actually 2 Cl's going to a -1. So it's actually 2 times -1, and 2 times -1 is -2. So it went from 0 to -2, which means I gained, or chlorine gained 2 electrons, okay? So sodium lost 2, chlorine gained 2, which makes this all balanced and everything equals out. You cannot just lose electrons to nowhere. You have to actually indicate where it is within the reaction. So our number of electrons transferred is actually 2 electrons transferred, okay? And the half reaction is going to help us. We're going to call it the LCM, the least common multiple between the two, in just a second here. Okay, so let's go through and let's just assign oxidation numbers to each one of these. Magnesium solid, 0. That's an easy one. It's on the periodic table, it's 0. Hydrogen, well, hydrogen's always +1 unless it's in peroxides, or I'm sorry, unless it's in hydrides. Oxygen's always -2 unless it's in peroxides, so that's a -2. What we don't know is we do not know what the sulfur is. So this sulfur right here is unknown. So what we're going to do is we're going to do this in 2 different ways. I'm going to show you. And so I'm just simply going to do, I've got my H2, sorry, I'm trying to get an arrow here. I've got 2 of the H's, and those we know are +1 each, so that's pretty easy. It's just 2 times 1. And then I've got my S, which is my unknown. I don't know what that is. And then I have my oxygens. And my oxygens, I have 4 times a -2 charge for each one. Now, because this is a compound, it has a value of 0 overall. It's a neutral compound. All of our compounds are neutral, whether they're acids or ionics or moleculars. Any of those are all neutral, okay? So what I have here is I have 2 plus S plus -8 equals 0. Well, algebraically, I'm going to solve for this. I know that if I add 8 to the other side and I subtract 2, then I get S by itself, and S ends up equaling a +6. Okay, now here's the other way of doing this that, in my opinion, is actually easier. So I'm just going to do this right up here. I know that SO4 sulfate has a -2 charge, but now it's an ion. Okay, now it's an ion. It's not SO4 compound. It is an ion. So I'm going to do the same exact thing. I know that oxygen is a -2 charge, but I need to figure out my sulfur. Okay, so notice I've pulled it out, but I'm doing it as an ion instead because I already knew H. All right, it saves you a little bit of time. Not much. Most of you will be able, and you don't even have to show this. If you can just figure out what the oxidation number is, just make sure you get it right. Okay, you don't have to show the algebra for it. I'm just doing it so that you can get an idea of how the algebra is working. So it's S plus, I've got 4 oxygens at -2 apiece, and this is all equal to -2, which means S plus -8 equals -2. And so if I add the 8 to the other side, so add 8 to the other side, I get that S is equal to a +6, which is exactly the same answer that we have here. So we can do it both ways, okay? SO3 minus 2 works out exactly the same way. So all I'm going to do is I know my oxygen's a -2, so S plus 3 times -2, which is -6, is equal to -2. So if I add 6 to the other side, I get, in this case, that S is equal to a +4. Okay, and if we looked at the periodic table again, we would see that that was one of our options for sulfur's positive charges. Here we go. We've got K2Cr2O7, easiest thing to do. We've got a +1, we've got a -2. You do have to label those as well. What I don't know is I don't know chromium, okay? Chromium can be a variable charge, so I need to figure this one out. I would rather pull out dichromate by itself. It makes it so much easier, okay? So I know Cr2O7 has a -2 charge overall, okay? So that means that overall, it's not equal to 0. If I did this entire compound, I would set the whole thing equal to 0, but I don't with this. So in this case, again, I know that oxygen's a -2. Now, it's 2 chromiums. So I'm going to say 2 Crs plus 7 times -2, 7 oxygens at -2 apiece, is all equal to -2, okay? Because that's the charge on my ion. All right, so now I'm getting 2 Cr plus a -14. I'm just going to add the 14 to the other side so that I get 2 Cr equals a +12. Well, then I'm going to divide by 2 on both sides, and when I do that, I get that Cr is equal to +6. And if you take a look at the periodic table, sure enough, that's one of the oxidation states for chromium. Okay, last one. Now this one, people will find a little bit more challenging, okay? Because they're looking at it and they say, oh my gosh, I don't know what to do because I don't know leads, I know oxygens, I know chromate, but I'm not sure what to do here. Old school, old school, old school. You know chromate is a -2 charge, okay? And if that's the case, -2, and I have 2 of them, means that lead must be a +4, okay? So lead must be a +4 in that situation. So when I do this, the only thing I really need to figure out now is my chromium, okay? Because people will say, yeah, but I don't know the lead or the chromium. Well, it's an ionic compound, so you do it the way that we did right in the first week of school when we were trying to figure out the Roman numerals. So that would be lead, Roman numeral 4, chromates, okay? So now let's figure out the chromate. Again, my recommendation is, especially because there's a 2 there, you would actually have to do 2 Crs and 8 oxygens. It is way, way, way easier if I just figure out chromates. So again, I know that chromate has a -2 charge overall, okay? And so I'm going to do that separately instead of doing PbCrO4 as a compound. It's way more algebra there, okay? So I don't know Cr, I know oxygen is -2 again. So I'm going to say Cr plus, and chromate in a compound and chromate out of a compound or in any compound, the oxidation states are always the same as long as it's chromate. So if it's dichromate, now it's different. It's always going to be a +6. So I've got Cr plus 4 times -2, 4 of them times a -2 charge is all equal to -2 because it's a polyatomic ion. So then I'm going to say Cr plus -8. So I'm going to add the 8 to the other side, which means I'm getting Cr plus 6 again here, okay? So then that would be my oxidation state of the chromium in both of those situations. All right, last thing here is an oxidation reduction reaction. So I'm going to do a part 2 to this. This is a great problem, and we will talk about kind of putting it all together for you. Happy day, everyone. I hope you have a wonderful day, and hopefully this was great learning for you.